My talk today is around, you know, Chrome and Chrome OS security, mostly focusing on stuff which is, we have done in the last year and what we plan to do in the next year or so. I wouldn't go into details about stuff previously, but happy to answer any questions about, security-wise that we have done in the past over the last, 7, 8 years on the Chrome and Chrome OS. Quick thing, I'm a member of the Chrome security team. You might have heard a bunch of my colleagues and stuff. So what we do as part of the Chrome security team? We do everything that's related to Chrome or our open source version called Chromium, right? Which means the Chrome browser. In the Chrome browser, it means on every single OS you have, your Windows, Mac, Linux, iOS, Android. We also focus on Chrome OS, whether it's a Chromebook, a Chromebox, or a Chrome base, and also Chromecast now. Personally, I focus more on Chrome OS, so that's there. My talk wouldn't have been possible without, this is just a highlight of all the great stuff that the Chrome security team has done over the years. And so it's basically sort of trying to give a quick summary of some of the recent work within the Chrome security team. So what are the core principles that we decided to design Chrome and Chrome OS by? There were three things, before we even created the first browser back in the day, there were three things we decided to do. There was speed, simplicity, and security. We basically decided that any feature we develop or anything we do within the product will have to sort of adhere to these three fundamentals of speed, simplicity, and security. So from the Chrome security team side, it was a big responsibility where security, which was sort of a core thing, was considered as one of the top three fundamentals of developing a product, developing a browser, developing an OS. So how did we come up and define what our initial principles was? The first principle that we sort of came up with was don't get in the way. Now, we have two other principles, speed and simplicity. We want to be very sure that we are not getting in the way of speed and simplicity, right? Because an important part is we can get security, but security is going to be completely useless if it's not usable, right? People are not going to use your secure product if they're not going to like it, if the UX is not going to be great, so on. So it's very important to ensure that you design your product and secure it in a way where it's very transparent, so it doesn't come in the way of the user. That's the key point here, right? Whenever you're designing a product, ensure that security is in the background, it just happens by itself. Couple of examples on the Chrome side are automatic updates where you don't have to worry about, having to click on dialogues or stuff like that, or the default settings for most of our things. It's like you want to ensure that it's sort of designed with keeping security in mind for every single piece of, the browser. The second one, you guys, as security professionals would have heard of this infinite times, right? Design for defense in depth, right? You have to do that at any product. But again, you have to keep in mind that we are designing in depth. It doesn't mean that you keep adding solutions that result in slowing down the user speed or making a really clumsy experience. So design in depth is good, and continue adding more things, but ensure that each defense or each exploit mitigation that you add actually is fast. It's not going to slow down the system. It's going to be actually something the user would not even notice. Another important thing as the Chrome security team was, it's not the responsibility of just the Chrome security team to keep the browser or the OS secure. We will never succeed that way. It was, decided that security or maybe privacy or anything else is finally a team responsibility. So every engineer that works on the system, every engineer that writes any lines of code, every QA guy, it's responsibility of each and every one of them, right? It doesn't matter, whether you have just, doing designs or stuff. If you're doing anything related to the browser, you need to ensure you keep these three principles in mind, and hence security also. Speed matters. Now I'm not talking about the speed of the product. but speed with which we respond from the security team side. Now, no code is really secure. So each code will have bugs, you will have vulnerabilities. How quickly as a team can you respond to them becomes the key, right? So if we get an exploit which we think potentially affects the users or is a 0 day or whatever, can you turn around time of less than 24 hours and push to hundreds and hundreds of millions of users? That's the goal that we set for ourselves. That within the time we find a vulnerability at that thing, can we patch it quickly enough and push it out to all our users transparently so that they are safe? Also be transparent. It's, when you get vulnerabilities or when you have stuff, there's no point hiding them. You need to ensure that you let the users know so that they can make the best decisions, right? So, for example, all our security design docs are public. Everything related to vulnerabilities, after we have fixed it, the bug goes public so others can learn from the mistakes we did while developing the software, but at the same time how we patched it. Another very, very important point is we can't do security in isolation. It has to be done as a part of the big community, right? Like the security community out there around globally, has some tremendous, tremendous people, and we can't really succeed or do anything without taking them with us in improving the product. Whether you're engaging them by vulnerability rewards or engaging them by making the code open source, it's important that you actually work with the community to make your product better. And the other important point is if you do something good and make safe, ensure that you're not just doing it for your own product, you're doing it for the world, right? Like if you write good, secure libraries or find stuff, ensure that everyone knows about it so that the web at the end of the day is safer for everyone. So that's sort of the core principles that we sort of set about with to do our work. Now, my talk today will focus on sort of three things, talking about Chrome browser security, some of the new stuff there, Chrome OS security, and then sort of talk about the vulnerability rewards program that we have. Again, I won't go into some of the stuff that we have already done in the past in terms of Chrome browser security. These are stuff like sandboxing, safe browsing, strict transport security, content security policy. You heard some talks about content security policy a couple days back, speedy, and so on. Just to get a hands everyone here, how many of you understand these four terms, HSTS, CSP, speedy? I see a few hands, okay. So I will then try to sort of give a quick one-line summary of stuff. So strict transport security ensures that you can basically get pages to do like ensure SSL or strict, you're actually forcing HTTPS over certain pages. Or when you're doing content security policy, you're ensuring that your JavaScript, you actually can claim which origins your JavaScript is running from. You can disable eval and so on. Happy to sort of, given the time I have, happy to sort of, anyone who has questions about these, go into details much after my talk. So what have been the new exciting stuff that we feel we have done? Partition alloc, JavaScript binding integrity, some more stuff around cert pinning, fuzzing, and site isolation. So let's look into each one of these. So one of the things we noticed when running exploit contests and so on, or like looking at the bugs that we received externally, a lot of them were use after free bugs that actually resulted into a full exploit. So what defense, how do you sort of come and protect against that? So one of our engineers in my team sort of came up with the idea of, right now you have a single memory heap that applies to everything in the browser. So for example, your DOM nodes or your strings, your array buffers, your renderer nodes, everything is of the same heap, right? So even if there's a use after free, you can use one type of object to basically corrupt the other type of object. So why not basically part, okay? So why not partition basically the entire, allocations for each object hierarchy into separate regions? Now, what will this do? How do you protect against this? So one simple way is you do it at a higher API level. Rather than at a lower level, you do it as an API level in the user space. You then ensure that each of the heaps are isolated from each other by, say, guard pages. You could do something else, but as a start, let's say they're just separated by guard pages. Now, what will happen? Once, say, an array buffer or something uses that heap for the first time, we can ensure that that space is allocated for it permanently throughout the system. So now if you're using, or actually let me take a different example. Say I have a DOM node, right, a renderer node in Blink or WebKit, and I basically allocate some space and there is a use after free issue. Now, if I am trying to use a string buffer to actually overwrite or like overwrite spray something around it, it will point to a different heap and therefore guarantee that therefore guarantee that you can't use a different object to corrupt another one. So right now in Chrome today, we have separate heaps for DOM nodes, separate heaps for rendering nodes, then a common heap for all the places where user has control, which is like array buffers, strings, vector backing buffers. Again, let me say this. This is just an improvement. It's not a silver bullet. It's not going to solve all your use after free bugs. It's just a way to sort of add another layer of defense, make slightly harder for the bug to exploit so that, you basically make it more difficult for the attacker. So this is, as for us, people who sort of work on the defensive side of things, each time you're trying to think about how can you sort of make it much, much more harder to sort of do it. And I'll sort of talk about some of our defenses and how that has meant that an attacker previously you could have found one bug to exploit the system, now needed 6 to like 15 bugs. So let's take the other case. Another case that we sort of observed was you had multiple Java wrapper objects, the Java engine and JavaScript wrapper objects, which is sort of, V8 for Chrome, both end up pointing to the same C++ object, right? So in this case, the JavaScript wrapper object A using a dangling pointer from X, is pointing to your C++ object Y, and at the same time you could have another object sort of B which was previously pointing to it. As a result, you could actually create a new wrapper object Z now to access Y and basically again use it as a case of confusion when you're moving from the JavaScript layer to the C++ layer. So what do you do about it? A new hardening feature that we added last year was add type checking between the JavaScript engine and the C++ object. So how do we go about doing this? Basically, when you create the C++ object in the previous sense, say Y, you actually store an unguessable representation of the V8 object type. Now, we can do that because of our ASLR defenses and basically store it sort of selected at the side within the C++ object. Now, whenever you create a new, so say in previous case, say some other wrapper C was pointing to it and the reference from C to Y got lost. Now we try to create another wrapper when an attacker is trying to make Z as a JavaScript wrapper object point to Y. Z will basically need to validate that type representation set in the C++ object, which it will fail to. And why it's okay to only do it at creation time and not at like every call? Luckily for us, in V8, the wrapper objects actually contain reference pointers back to the C++ object. So you can ensure that that is still in memory and you don't have to keep checking on every single call. Otherwise, the performance risk would be high. Now, there's a downside to it. You don't end up sort of fixing some of the heap corruption issues or something else, but at least you take care of 70 to 80% of the attacks there. This, we got it in last year. Had we got it in like 2 years back, we could have actually stopped a couple of the entries at Ponium and Pon2Own from last year. or from year before last. So the next one is improved certificate pinning in SSL. So I talked about stuff that we had done in the past with HSTS, and we also had pinning. So you could actually say that only these 2-3 root CAs are valid for a particular domain. But what we were worried also was, especially when you're accessing Google services, is what happens if my root CA gets compromised, right? We have seen that, right? We saw that in Iran and a couple other countries where the root CA was compromised. Now, does that mean that my whole connection gets compromised? So what we decided is we could actually pin it to the intermediate Google CA. So even if a root CA gets compromised, because we are actually checking the pinning to the intermediate CA, someone, if trying to do a man in the middle against a Google sort of domain, will get caught by Chrome. Some of the other defenses that we added was, added support for TLS 1.2. I wouldn't go into details about, AES GM cipher. We actually start using it for Google properties. And also, with sort of the worry of, RSA 1024, a lot of our Google properties move to sort of 2K keys. So over the last, we had safe browsing, right, where Google actually goes and checks every single website to know if there is malware running on it, and then actually blocks it, right? So it has both phishing as well as malware blocks. So you would see sometimes a red page saying this site has potential malware, do you really want to continue, or whatever. Similarly, in the case of when you're downloading certain downloads, it will basically say, we think that is malicious, do you want to run it or not? Over the work that we have done, research over the last few years, we are now so confident about our ability to be sure and not have any false positives that we don't even give the option anymore to the user. We actually are confident that this will have a malicious download out there, so we don't make it click-throughable. We can actually block. So from an end user perspective, this is going back to a principle of, don't get in the way. If if you have got your certain level of confidence, go ahead and block it. Other thing is, we've seen a bunch of bugs in the past with, PDFs and reading stuff. So we had a PDF, we basically have an inbuilt PDF reader, which is well sandboxed using the same principles, first well. So we now can also ensure that from your download shelf in Chrome, whenever you click on a PDF, instead of opening up in your default PDF reader, can open up in the sandbox Chrome. Again, giving you additional security out there. Another big source of, I would say, malware out there was using NPI API plugins, right? Everyone knows here the history with plugins and how plugins can go and, cause harm to your devices because it has full control, right? It's like any binary with full powers without being sandboxed. We decided to sort of block NP API by default from an end user perspective, because everything they need to do in NP API could be done with proper apps and stuff. So it was, from an end user securities perspective, better to block it. So how many of you have done fuzzing? Half of you? Okay. So as all pen testing or anything related to security, like fuzzing becomes a very, very important attribute to try to find out bugs and sort of detect stuff that is sort of wrong on your device. We had to do the same thing with Chrome. So the idea was to create like a fully automated crash detection system that could take a crash in Chrome, analyze it, see if it is a security issue, and not just, sometimes we get issues that crashes could be like from files which are megabytes in size. How do you reduce it down to the smallest minimal size so that you can easily reproduce it? And if you have the system in place, then every single line of code that a developer checks in, we could basically run our whole tool, right? If you have this whole fuzzing tool. So right now, we basically designed this cluster first, which actually runs of around hundreds and hundreds of virtual machines at the same time, giving like thousands of Chrome instances running with probably millions of test cases being sort of run through every single day. What that basically means is it, and sort of to add, it runs on multiple platforms that we support, which basically means is every time uh, today a developer within Google or within the Chromium org, because it's sort of, anyone externally also checks in a code, we will basically go ahead, run our whole set of test cases to ensure whether there's anything wrong with it. But how do you ensure that tests are actually failing? How do you, catch or use after free errors? One of the things we do is all the builds that we run, we instantiate with what we call as the address sanitizer. So what is the address sanitizer? In the address sanitizer, you can actually poison your malloc and free to ensure that if, someone is using it after it was supposed to be freed, you can actually now catch it. So that's not great for production builds because it will slow down the system. But in your fuzzing system, you can actually basically run that, and that is a great way to catch coding errors as well as security bugs. So this is the one big reason we have able to catch over 1,000 bugs before they were even released to the user, right? And so this is sort of the advantage of actually running this kind of fuzzer at this scale across so many devices. There's a lot more planned code coverage, integration with Clang tools. You guys can also sort of, all the cluster first code is open source. So if you guys want to use it on your own systems or, submit test cases, you're more than welcome to do that. So let's talk about what is the state of sandboxing today. Just to give you guys sort of things. So today, every Chrome browser renderer runs in a restricted sandbox, right? The sandbox does its defenses and stuff. From a Chrome browser perspective, it will make a best attempt to keep every domain in a separate sandbox. So for example, your A.com, B.com, and C.com are in a separate sandbox, a separate process. But that unfortunately doesn't always happen. And the reason for that not always happening is a few things. What happens with cross-site iframes, right? Now, if I cross-site an iframe from A.com to B or C, it would potentially be in the same sandbox because you're not spawning a new process when you're doing a cross-site iframe. It could also happen where you're doing some renderer navigations, like submitting a post form. It could mean that you're now potentially having multiple different sites, which could be trusted or could not be trusted depending upon how the developer has made it within the same sandbox. At that time, currently, we actually rely on the renderer doing the right thing by sort of, ensuring the same origin policy. So we are still, following the browser principles of same origin policy, but it's not, there's still room for someone to override it. So site isolation is a project we have been now working for multiple years of how do you sort of get to the minimum subset to guarantee that every single domain is in a separate, completely separate sandbox, completely separate process. Why will you want to do that? Because now your cross-site, cookie leaks or any of the other attacks that you have, now you can prevent against that. You can basically increase your web security by a humongous amount, in my opinion, if we can sort of reach that. So what have we been doing? We basically came with this site per process policy that can ensure each renderer page contains page from at least one website. Now, we have to do some assumptions because a lot of the web works by doing, post messages and stuff between their subdomains. So we sort of try to define what is the minimum unit, which we call as the site instance, that needs to be sort of in their own sandbox. Our point is that anything of the same main domain, so subdomains like www or foo.a.com will be in the same site instance, but anything related to B or so on will be another one. This basically now helps us ensure once we finish this is still a work in progress. Hopefully we can land this sometime in 2014. It can basically help you against cross-site iframes, too many renderer issued navigations, to still ensure basically protection at a secondary level in addition to the same origin policy that is already there. let's move on to sort of Chrome OS security stuff. So focus here is on, sort of, I talked about stuff that we have done browser and above. Let's see of what we can do below the browser to sort of make a device that's more comfortable. The whole idea, at least from us security guys, was we were uncomfortable using devices at that time, right? One of the things for most of us folks in the team was, can we, if we are building a new OS or whatever, can we build an OS that we would be comfortable to use it, comfortable to take it to DEF CON, NullCon, wherever, without the worry of being hacked, right? That sort of was sort of the goal and idea about doing this. What can we do to make it as secure as possible? Now again, nothing is fully secure, but what can we do to improve the defense out there for my device? So first of our ideas was verified boot. Now everyone knows about what a ROM is, right? It's a read-only piece of memory. You cannot tamper it unless you open the hardware and do it. So the whole idea of verified boot was to protect against persistent remote attacks. Now remote is important here because we're not so worried, or that's not in the threat model of sort of protecting against someone who has stolen your device completely and is trying to put malware on it, because they might as well just replace your spy flash or replace your hard disk and give you back the device. That's a different story. But you want to guarantee that when I'm browsing the internet, or when I'm in a coffee shop, nobody has the ability to completely put a persistent malware, a persistent rootkit out there. So we use the age-old simple phenomenon of having that, ensuring that the entire root of trust is in a read-only memory. So the main firmware is completely unwritable in a read-only memory. Once the read-only firmware is, so an attacker cannot remotely change it because it's actual read-only memory. You can't by software make it read-write. Now, once the read-only firmware is there, during boot, it can check the mutable or the read-write firmware. And to ensure that there are no bugs in the read-only firmware, you keep your parsing to a minimum. So just ensure that a proper signature is there, a single small check, and that's it. Now you can have all your firmware, boot initialization code in the read-write firmware, which you can update over time and so on. Similarly, once the firmware has been checked, it can then sort of validate the OS and kernel and the boot data. Again, trying to keep at a minimum of what it can pass, like partition tables in GPT or like kernel headers. And then, of course, validate the file system. So how does this work? We have the read-only firmware that, during boot, when you press your power button, the read-only firmware will run. It will go ahead and verify the read-write firmware. The read-write firmware will basically then verify the kernel header, pass the GPT tables, and you'll verify the kernel partition. And once that has been done, it will then verify the root block device. I'll sort of come into the details of how the verification of the root block device happens, but this is how the process is. It's as simple. Like, there's nothing, great there. The only thing was this theoretical idea, which has been there for ages. How do you actually bring it into a device and make it for consumer use, right? So what this is guaranteeing is that on boot, we are checking every single bit of the operating system at boot itself, right? So because you're checking every single bit before it is run, you can guarantee that even if there's malware, you can actually catch it. So what happens where, say, in the last time something had happened, someone actually went and modified the kernel partition. In this flow, the read-only firmware will verify the read-write firmware. But the read-write firmware, when it checks the signature for the kernel partition, will see that the signature doesn't match. For Chrome OS devices, we actually have 2 copies of the operating system running at or 2 copies of the operating system on disk. So it can try and check the backup partition to just give you some form of redundancy. But if both of them don't work, it will just not boot the device and let you do a safe recovery, directly from the read-only firmware. So at least guarantee you that when you're recovering the device you're doing today for another device which doesn't have the static root of trust, If I am reflashing the device, how do I know my firmware is not corrupted? And how do I know that what I'm flashing is actually happening? Right? With this, because everything is starting from the hardware, you can actually guarantee that. Let's look at sort of the stuff of how the kernel and the system below works, because there's sort of some of my colleagues have done like great work out there. Um, the challenge now is, our goal, as I mentioned, was to do it fast. So the goal was to ensure that a boot time was less than 10 seconds of the entire operating system. Now, how do you boot in less than 10 seconds and still do all these signature checks? Just to give you an idea, actually taking a slide back, the signature check on the read-only firmware from the read-write firmware is like a 8192-bit RSA key. The one on the read-write firmware to the kernel partition is 4096-bit RSA key. And the one from the kernel partition to the root block device is 2048-bit RSA keys. So we are dealing with, huge keys. So we need to ensure that even with using that high keys, we still are fast enough to ensure that the boot is in less than 10 seconds. So the idea was, the goal, the thing was, it might be okay if we don't sort of check every single bit in that first 10 seconds for the root file system, so far as we can ensure that we can check every single bit before it is run or executed the first time. So the idea is, you pass in the kernel command line your parent hash for the root file system, which then the kernel can use to sort of verify a second level of hashes and make like a complete hash tree. Now, when any block of device is actually read or used from the file system, it will first check whether it match. It will take a hash of that block and match it with the hash of hashes that was already verified at boot time. So you can actually guarantee that any code of the operating system that gets run gets verified whenever it is run for the first time. Again, it's built on device mapper, compatible with other sort of trusted boot solutions. We have seen, this, we call this DM Verity, which has already been mated to the Linux kernel, and I know of a bunch of other distros and stuff which are already using this now. You can enable it for them. So in the last talk, we sort of talked about, encryption is not necessarily enabled by default for most users. How do you change that? How do you, again, ensure that you make it default, secure, and you don't get into the way of the users, right? So the idea here was to ensure the most private data user has is generally their data, so user storage, right? So it could have your PII, it could have even sensitive PII information there. The goal was to ensure that every user's home directory was default encrypted. And the idea would be is to basically ensure any data which is in user's thing is protected. How do you ensure that you protect the data, but at the same time also prevent against brute force protection and many other things, right? Your device, my SSD gets stolen or my device gets stolen. How do you protect my user data? At the same time, we wanted to ensure that somebody else can't say and make a case and get my data sort of. So we basically, for the base layer of encryption, used 128-bit AES symmetric encryption. But the idea here was to ensure that the first level of keys is actually encrypted on disk by another sort of keys which are high 512-bit keys and RSA 2048 keys, which are actually derived from the TPM on the disk. So each Chrome OS device that gets shipped actually have a security chip TPM in it. So it device on from the TPM and also from the user's password. So what guarantees does this gives me for all my user data? It basically means that even if someone basically takes, steals my SSD out of my device, they need two things. They need to somehow be able to carefully take out the TPM, extract the keys from the TPM, and at the same time know my password. So basically add like 2 layers of defense out there to actually protect my data. Also, another interesting thing with the TPM is, given how much time it takes from TPM to sort of, do operations. Because remember, it's not just removing a key out of the TPM, you actually have to end up doing operations within the TPM. Given the speed of the TPMs today, that sort of gives you brute force protection also, because you can at the max perform one operation in around a half second or a second. So you basically are guaranteed that someone can't result in like million password checks in a minute or so on. Also, the other part is system data, right? There's probably no private data in there, log files and stuff, but we also ensure that we use keys from the TPM to protect your system storage. The whole idea at the end is sort of all data at rest is encrypted and sort of, reducing your risk. One thing I sort of skipped mentioning was right now a system storage uses dmcrypt while our user data uses encryptfs. And why the two? Well, we actually were doing dmcrypt initially, like 4 years back for user data, but the performance wasn't great. Especially at the time of a logout, closing everything took multiple seconds there, which was too slow to make it, not transparent. So we moved to encryptfs, has served us well, but given the improvements of dmcrypt over the last few years, one of the things we plan to do is sort of evaluate dmcrypt again because it has some other advantages over encryptfs. Now, so you've prevented against persistence. You have protected against your data on disk. Now, the next step is you want to harden your operating system. Luckily, on the Chrome OS security team side, we are responsible for the entire stack, right? We are responsible everything from your firmware and embedded controller out up till Chrome. So how do you do that? Like, now, there are a bunch of system daemons. You want to ensure that each of the system daemons does the right job in setting capabilities or so on. To be very frank, having worked, you won't end up getting many developers who will do that. So what do? You end up writing like a privileged operator helper utility, which we internally call it as mini jail. That sort of does a bunch of the standard, kernel level hardening or user level hardening stuff. Everything from applying Linux capabilities to user group changes to PID VFS namespacing to so on. Like it basically does everything for you. All you now need to do is every daemon or service that gets loaded with an LD preload for this library, and then it will sort of set the rules for it correctly so that you can reduce your capabilities of the system. What else do we do? The standard compiler, user space, and kernel hardening, like all your stack protector, ASLR, DEP, trying to basically ensuring the kernel pointers are not leaked out, all the basic stuff. Like when you take any device of yours, like even semi-secure kernel or Linux-based device, you will do all this stuff. But what's the next step? Like everyone does that. What else can we do? Idea was to ensure that we have a completely read-only root file system. Most users, once the operating system is done, they don't need to go ahead and like modify or make changes to your core where the OS is. So you can make it a read-only root file system. You can also ensure that if kernel modules are loaded, they are not loaded on the fly by an attacker, but they're only loaded from the read-only root file system. Right? This would have been not really useful if the root file system was not read-only. Similarly, you'll have device firmware also limited to that. Our device doesn't really use hibernation, so you can actually disable hibernation and KXEC. Disallow option ROMs, add more mount target restrictions, and sort of harden your glibc so that you can basically add more and more layers of protection out there. How much time do I have? 5 minutes. Okay, so for people familiar on the kernel Linux side, there has been the seccomp legacy stuff which would allow you to filter, read call, write call, sig return, exit. The problem was this: it was a very tight sandbox, but it was too restrictive to use in practice. What that really meant is most people really couldn't use that for sandboxing unless it was like specific cases. So the idea was to sort of come up with a more generic sandboxing in kernel that would not only sandbox the system services, but also give a second layer of sandboxing to Chrome. So we basically, I'll skip through the history of how we came up with this, but the idea was to end up using Berkeley packet filters, BPF as they call it. So BPF today is used for network packet filtering on Linux. The idea was how can you use some of the same principles to do actual security filtering. So one of the big advantages of BPF is there are no loops. It's a simple decision tree that you can actually make decisions out of. You can now use it by making a call as like a system packet call and its arguments and give it to that and then make a decision according to that. So it can use to inspect like system call arguments and also basically ensure that pointers cannot be followed. Once I sort of create rules for my device, then I can ensure that I can either kill the process, return an error, trap, identify which calls are there, log them, and so on. So where are we using this already? It's already in kernel upstream. We are using it in the Chrome renderer. So along with the setuid sandbox that allows you to block file system or network calls, this allows you to basically provide a further level of attack surface reduction. We also have a GPU sandbox on Chrome, so that GPU is sort of another great source for bugs. So we have a GPU sandbox which is completely written on seccomp BPF. There it's interesting. The seccomp BPF is used not just for attack surface reduction, but also for your access control semantics. The way we do that is we use a helper process for the GPU, which sort of intercepts every single call, and you can sort of verify and validate there before you pass it on. All services that access like USB and stuff on Chrome OS use this sandbox, and so also like the mini-jail support that I mentioned earlier. Sorry guys, I'm just trying to run through given the time here. Another thing that we landed last year, so everyone knows about ASLR, everyone knows how ASLR is done in the user space. Unfortunately, there was no concept of kernel ASLR on Linux. So we basically decided that it was okay, sort of work towards that and add kernel ASLR to Linux upstream so that we can actually randomize where the kernel boot code is there at boot time as an additional layer of defense. There are some limitations where we are only doing it for kernel code right now and not for stack and heap and stuff. But again, it's a start and we hope to continue to sort of improve there. There are a few limitations of kernel ASLR as it is today, where it doesn't support hibernation, but doesn't matter us for Chrome OS because we don't use hibernation. But again, adding hibernation support is not a big deal. Someone can sort of add to it. Another thing is sort of entropy. Given the 2 megabyte limit size of the kernel, there's some limitations there. But there are a few things we could do to actually make it useful, and that's what we're doing on Chrome OS, where we actually ensure that we enable kernel pointer restrictions so that we are not leaking kernel pointers. Dmessage is another place where addresses can get leaked. So use the dmessage restrict thing to not leak addresses. Ensure your log files are not leaking addresses, and also ensure your like ape kernel objects are not leaking. So avoiding address leaks becomes a very important thing to sort of support the kernel ASLR work that we do. This is sort of simple stuff. Walk the E820 regions to sort of identify randomly sort of what is the best place to put it. You can use hardware functions like RDRAND or anything else to basically randomize which location we are actually putting setting up the ASLR with. We don't support ARM yet. It's only Intel support added. For ARM devices, we hope to add support again this year. Another sneak peek, as with site isolation in Chrome, verified access is another interesting thing that we have been working now for the last year and a half on the Chrome OS side. So a couple of problems that normally come up is corporate network resources, right? How do you guarantee stuff that you're accessing it from actually a corporate device and not from any other device, right? How do you get those kind of hardware guarantees and not necessarily software guarantees? How do you sort of make the AV vendors happy with premium content, which is like full HD content? So TPM, which is present on every single Chrome OS device, already contains protected keys that you can are present there. What we can do with verified access is now actually validate them with an anonymous service, so your privacy is preserved, and then give you sort of validating certificates that you can give to your corporate authority to actually guarantee that this is coming off a device which actually has a valid TPM and operations are getting signed inside the hardware in the TPM. So it's a feature that we have been requested a lot by enterprises, and I think once we sort of actually give it out, would be sort of, we are already sort of dog fooding this internally. So sort of running it and coming to the security rewards program. So actually, before I go that, how many of you have heard about the Chrome or the Google security rewards program? Almost everyone. That's good. So do you know the different type of rewards programs we have? The Chrome rewards program, the Google rewards program. Anything else? Anyone? Okay, comes under the Google one. Anything else? That's fine. So why do we do the security rewards program in the first place? The goal is twofold. First is, of course, better protect our users. Vulnerabilities come in, we can patch them, we can be quick, we can have a quick turnaround time and ensure our users are safe. Given our automatic updates to like Chrome and the ability of our web services, we can do that rather quickly. The other thing is to build relationship with security researchers, engage the community, ensure that we are using the talent of everyone and not just a few people. So we have two VRPs previously, which was the Chromium VRP and also the Ponium project that we do. So the Chrome or the Chromium VRP covers your Chrome browser, your Chrome operating system, some third-party software which are part of the Chrome browser or the Chrome operating system, and apps and extensions that are done by Google. Google VRP covers like some of the top Google sites. But wait, there's something more that we announced very recently, which is we don't want only you guys to find vulnerabilities, but also to go ahead and find patches, right? Actually solve the problem, because you can just find vulnerabilities. We want to sort of help the overall community here. So we are saying if you find and patch security issues, not just for Google products, but for all like security critical components of Linux kernel, all your open network libraries like OpenSSH, OpenVPN, so on, your mail servers like Apache, HTTPD, so data parsers like libjpeg, libpng. So anything you do and you actually submit patches, we will actually pay you for that, because we want incentives for people to go ahead and not just find bugs but actually fix them. As an announcement, we have already sort of given out $2 million in like our VRPs. The prize money used to be like 1K for the biggest bug. Now it's up to like 5K or so on. And for those who are not familiar with Ponium, it's a contest where we actually put big money at a conference. Last year we put up like $3.14 million for Chrome OS. This year we're again putting up $2.7 million. Like last time was Pi million, this time is exponent million there. So for some of you, I saw some of you at CanSec last year, but if you're at CanSec again next month, we'll again put up both x86 and ARM devices. Again, the idea here is not necessarily to like show it off, but more to ensure that we learn from even partial bugs, right? Just to give an example, in a Pon2Own vulnerability for the Chrome browser on Windows that happened 2 years back, people had to find, there are two separate bugs. One had to find 6 separate bugs to actually take from something to an exploit, and the other 14 bugs. So this actually helps us improve the product. I think I'm out of time, but that's the core principles. I ran through a lot. There is references here. You can go and sort of read up more about it. Everything is there. And thank you.